Nuclear magnetic resonance spectroscopy, which is usually just referred to as NMR, is a type of spectroscopy. And what that means is you're shining light on a sample and you're identifying what's in your sample based on the shadows that are cast. We've seen a type of spectroscopy before. It was IR spectroscopy. And the type of light that you used was infrared light. If you remember, light is a wave in the fabric of electricity that permeates through all space. Just like if you move your hand up and down in water, it creates a wave. If you move charge up and down, it ends up creating not a water wave, but a wave of electricity in that fabric of electric charge that interlaces itself between all the protons and electrons, all the positive and negative charges in the universe. Different types of those waves are separated, categorized, based on how frequently the waves hit you. Because the more frequently waves hit you, the more energy they carry. Just like if you stand in the ocean, water's hitting you one wave after another, it's carrying a lot of energy. The more frequently the waves hit you, so likewise with these light waves. So they classify these waves based on how much energy they have, because the amount of energy they have determines what they can get done. And so you have these different regions with different amounts of energy based on how frequently the waves would hit you. And so infrared, that was those frequencies which are a little longer, or a little lower. They don't hit you quite as often as visible light. Those frequencies are what we shined on molecules when we did IR spectroscopy. And the shadows were cast because dipoles vibrated differently. Instead of the light going through the sample, the dipole would start vibrating differently, and so what was a wave of electricity turns into the vibration of a bond. And so the light doesn't keep traveling, it gets absorbed. And the information we got was about the type of dipole we have. In other words, we were able to tell what functional groups were in the molecule. So let's compare this new type of spectroscopy, NMR spectroscopy, with that. So here we're dealing with something called nuclear magnetic resonance spectroscopy. We'll break that down in a second. The type of light we're going to be using has much lower frequencies. In other words, it's carrying much lower amounts of energy. Here we'll be using radio waves. Infrared waves, for example, could hit you at around 300 trillion times. 300 trillion waves hitting you in 1 second. A trillion. Radio waves could be around 30 million waves hitting into a second. It could even be as low as just 30 waves hitting you per second. Radio waves hit you much less frequently, and so they carry much less energy. As we'll see, the shadows are going to be cast because nuclei will flip in a magnetic field. We'll break that down in a second. That's the general idea. And the information we're going to get here is how atoms are put together in the structure. Basically, we're going to get the structure of the molecule. So here we just knew what functional groups are present, but now we can use NMR to take a molecular formula, something that we might have gotten by doing mass spectrometry. You get the molecular formula, and you can do NMR to figure out how those atoms connect. You get a lot of information out of it. It's very useful. So let's talk about this, how nuclei flip in a magnetic field. What does that mean? So anytime charge moves, it creates a magnetic field. Let's say you had a proton. The proton in the nucleus isn't just sitting still in a nucleus. It's knocking against the other subatomic particles in the nucleus. It's spinning, it's rotating, it's bouncing around. When that positive charge moves, when it spins around, it creates a magnetic field, and I'm going to draw that in as a little bar magnet. So it acts like a little bar magnet with a north and a south side. Whenever electricity moves, it creates a magnetic field. So already we can start to see why nuclei have a magnetic field. Each of the protons moving around in them has their own tiny magnetic field. Now, if you have an even number of protons, then they'll line up to cancel each other out. So the two protons that would pair up, their magnets, little magnetisms, their bar magnets would cancel each other out. So you'd have to have an odd number of protons in order for the nucleus to have a magnetic field. There is another option, though. Even if you have an even number of protons, the nucleus could still have a magnetic field, and that's because neutrons also act like little bar magnets. You might say, wait a second, why? We got this bar magnet because a charge was moving, and neutrons don't have a charge. But neutrons you can break neutrons apart. Neutrons can be broken apart into two pieces, and actually, if you think of the different pieces in an atom, it's interesting to see. You have electrons, protons, and neutrons. The electrons can't be broken apart. Those are stuck together. But the protons and the neutrons can be broken into smaller pieces. All the smallest pieces that you could never break down in the universe, those are given in a table called the Standard Model of Particle Physics. So this table has all the different pieces, the smallest pieces you could possibly have. You can't break things down smaller than this. Everything is made up of combinations of these things. You notice the electron is one that can't be broken down. But the protons and the neutrons are just made up of two of these quarks. They're called up and down quarks. Take a moment to appreciate all of chemistry is just talking about these three particles. But in the world, you have this whole table. So the protons and neutrons are made up of smaller pieces. The protons end up being made of two up quarks and one down quark. And the neutrons end up being made of two down quarks and one up quark. And the quarks are swirling around in the space that we think of as the protons and the neutrons. Now, it was already clear to us why the proton creates a little magnetic field and acts like a bar magnet. It has a charge overall. So we'll not consider that for right now. Let's think about the neutron. So the neutron, each of these quarks has a charge, and it has a mass. The down quarks have a charge of -1/3. So that's a third of the charge on an electron. And we have two of those. Each of the up quarks has a charge of +2/3. So you can see that the charges overall cancel out, and the charge on a neutron is 0. But the magnets, you see that these quarks have a charge. They're moving around, so each of the quarks are going to produce their own little magnetism. The magnetisms are not equal. The magnetisms don't cancel out because the down quarks are heavier. The up quarks are lighter. And when you make this massive thing with charge move around, it ends up creating a stronger magnet. So these would be like big, strong magnets. And those move around. And the other charge, the opposite charge, true, would go in the opposite way. But even though it has twice the charge, because this is lighter, the magnet here is not as strong as the other two. So when you add up the magnetisms of these things, there is magnetism left over. So when those three things fly around, their charges cancel out, but because one of them is heavier. When it spins, it creates stronger magnets. And so a neutron also will act as a bar magnet with a north and south side. Now, if the neutrons pair up, just like with the protons, if you have an even number of neutrons, then their little bar magnets will cancel out. And you'll have no magnetism overall. But if you have an odd number of neutrons, in a nucleus, then you'll have an unpaired magnet, and the nucleus as a whole will have a magnetic dipole on it. Okay, so let's summarize what we just went over. We just determined that if a nucleus has magnetism, it behaves like a little bar magnet if you have an odd number of protons, because then the little bar magnets don't all cancel each other out, or an odd number of neutrons. For the same reason, the little bar magnets on the neutrons don't cancel each other out. Okay. This magnetism is crucial because the whole reason why we went through this is because we're going to use this magnetism to absorb the radio waves, the light that we shine on things, so that we can only see nuclei that have this magnetism. It's only those that are going to cast shadows in this type of spectroscopy. So if you think about individual types of atoms you could have, imagine you have hydrogen 1. You have 1 proton, 0 neutrons. Well, we have an odd number of protons. So that means this does have magnetism. So we're good. How about carbon? Let's compare several isotopes of carbon. Let's say you have carbon 12 and carbon 13. Carbon 12 has 6 protons, 6 neutrons. All of the little magnets and the protons pair up and cancel each other out. North, south, south, north. Cancel each other out. All of the neutrons do the same thing, cancel each other out. A carbon-12 nucleus will not have magnetism, and so we would not be able to see that in this type of spectroscopy. In carbon-13, 6 protons, that's what makes it carbon, but 7 neutrons. Notice we have an odd number of neutrons. That means that we will have magnetism. And so we would be able to see carbon-13. And just for the sake of comparison, you could use, for example, fluorine-35. That has an odd atomic mass. That means you have either an odd number of protons or an odd number of neutrons. And so you would be able to, so the nucleus has that little bar magnet, and so you'd be able to see it. It would cast shadows in this type of spectroscopy. Okay, so that's the first thing. You can do this spectroscopy with any element that has an odd number of protons or neutrons. Now, what we're going to focus on, just for the sake of clarity and simplicity, is a type of, is our nuclei for hydrogen 1. So we saw you can do this type of spectroscopy with almost anything on the periodic table. Just pick an isotope that has an odd number of neutrons or an odd number of protons. But we're going to focus on hydrogen 1. So each of these hydrogen 1 nuclei, there are a lot of, and we're doing this because there are a lot of hydrogens in these organic molecules that we deal with. So we're going to get a lot of shadows. The more shadows that are cast, give us more information about the molecule. Okay, so imagine you have a bunch of different hydrogen atoms, and each of those have their own little bar magnet nucleus. And normally, those would just be pointing in random old directions. No reason they would all be in any way specific. They would just be random old directions. Each one in its own place. You can take these, and as they are, they wouldn't absorb radio waves. Shine it through, and the radio waves do nothing to these. But we can create, artificially, we can create an environment that radio waves will be able to affect. What you do is you take a strong external magnet and you apply it here. You put these in the middle of a magnet, and that strong external magnet acts like a gigantic bar magnet with a north side and a south side. And when that happens, most of these little nuclei will line up so that their south sides are facing the north side of the magnet. Most of them will line up like that. But some of them, a little less, will have more energy. They're bouncing around, the nuclei are vibrating, they're knocking around, they've got more heat. For whatever reason, they have more energy than the other nuclei, and so they need a way to express that energy. And the way that they do that is that they go into an alignment that is opposite the magnetic field that you're applying. So notice, we have this north side going here, so it's natural for these to have their south sides lining up with it. In other words, these are parallel to the bar magnet, to the external magnet we're introducing. Those are parallel. The next most stable way that the nuclei can go is anti-parallel. So the north side faces the opposite direction as the external magnet. And you can see why that would be the next most stable way, because imagine you have a bar magnet that's in any way horizontal. Then the external magnetic field will push on it in two places. It'll try to make it spin by pushing on it in two places. At least when it's anti-parallel, it only pushes on it in one place. So you have these nuclei now not randomly oriented, but oriented in two positions. The parallel position, and the fancy term for that is called alpha. So these are all in the alpha position. And the anti-parallel position, and the fancy term for that is called beta. So that this last one that's anti-parallel is in the beta position. So now we have two states, and we can graph this as a function of energy. You can say, okay, imagine you have the energy increasing. The most stable way for the nuclei to exist is in the alpha way. They're in line with the magnetic field. South side lines up with north side. Everything is good. At a higher energy, it flips to the beta. So there's a certain amount of energy, there's an energy difference between the alpha state and the beta state. And this energy difference is the energy that can be absorbed by radio waves. So you'd shine radio waves, here in purple, you'd shine them onto this nucleus, and the nucleus flips so that it's anti-parallel. And then once you stop shining the radio waves, it flips back. And you shine the radio waves again, and it flips. And then you stop shining the rays and it flips back. So the radio waves are being absorbed when you flip these nuclei in the presence of an external magnetic field. Okay, well, where we are right now is we can tell whether hydrogen exists in a sample by applying an external magnetic field and shining radio waves through. And if the nuclei flip, they'll cast it, and if the hydrogen is there, it'll cast a shadow, the nucleus will flip and it'll cast a shadow at the frequency of the wave that has the same amount of energy as you need to go from this alpha quantum state to the beta quantum state. But that's not particularly useful. By the time you do NMR, you've probably already done mass spectrometry, so you already have a molecular formula, and you would know you have hydrogen in your sample. So why go through all this trouble? How can we get more information from this, aside from just knowing that hydrogen is somewhere in the sample? And the answer to that comes from electrons. So far in our discussion, we've just talked about the nuclei. And actually, we've gone far enough in the discussion that we can appreciate the name of this technique, nuclear magnetic resonance spectroscopy. The nuclei are like little magnets, and we're shining light on them until the energy of the light has the same amount of energy, in other words, is in resonance, the same amount of energy as the difference between the two states. When the light you shine has the same energy, it's said to be in resonance with it, with the energy difference, and so the nuclei flips, and we get our shadows. Spectroscopy. Okay, so far we can tell that hydrogens exist in a sample, but that's not particularly useful information. We can get more useful information by when we add another particle in here, a particle we've neglected so far, and that particle is electrons. So far we've only considered the nuclei all by themselves, but of course the nuclei have electrons flying around them. Now, magnetism fills a space sort of like a spring fills a space. If you have a spring is at a certain equilibrium. There are forces pushing it out and pushing it in, and the forces match each other when a spring is still. If you take a spring and you try to push it in, the spring will push against you. If you try to push it in, it'll resist the change, it'll push back out. If, on the other hand, you try to pull the spring out, the spring resists the change, it'll pull back in. So it fills space in a certain way, and when you try to change the way it fills space, it acts to resist the change that you're introducing. Magnetism does a similar thing. When you introduce this, the magnetism of all the particles in an atom has a certain arrangement in space. It fills space in a certain way. And when you introduce this big bar magnet, this external magnetic field, when you introduce that, it is trying to change the way that the magnetism is filling space. And so just like the spring, the magnetism that already exists in the space it moves in such a way as to resist the external magnetic field. Now, how does it do that? Well, it does it with electrons. Electrons can fly in little loops in their orbitals, fly in little loops. And just like if you were to have a wire and you pass electricity through it, and you sprinkle iron filings around it, the iron filings will line up according to a magnetic field. So you'll be able to see the magnetic field through the loop. So in other words, if you have electrons traveling in this circle, they create a magnetic field through the circle. And electrons can travel in little loops like that in their orbitals. So what ends up happening is when you introduce this external magnetic field, the big blue one at the right, the electrons around these nuclei will fly in such a way that they produce a bar magnet that opposes the external magnetic field. So I think this is actually a little clearer if we use arrows. Imagine the external magnetic field being magnetism pushing up. The electrons would fly in such a way as to create create their own magnetic field, because whenever charges move, they create magnetic fields. So when these electrons move, they can create a magnetic field, and they create one that opposes the external one, that pushes against it, just like a spring pushes against you when you try to squeeze it or when you stretch it. Okay, now, the key thing to notice here is that the magnetic field felt by the nucleus, is the sum of the external magnetic field plus the magnetic field of the electrons that are pushing against it. Okay, so let's look at two scenarios. Let's say you have very few electrons. So let's say just a couple electrons flying around. When they go in a circle, they will create a magnetic field that opposes the external magnetic field, but it will be small because it's not a lot of electrons. Then, imagine another nucleus that has a whole bunch of electrons. When they all travel in a circle, they create a stronger magnetic field opposing the external magnetic field. More electrons moving around creates a stronger magnetic field. And the magnetic field felt by the nucleus is the sum of the external magnetic field plus the field made by the electrons opposing it. So, imagine these two cases. In the first case, when you have few electrons, when you you add these up, you end up with a magnetic field that's still relatively strong. That's this one right here. When you have a lot of electrons, you add those up, you end up with a magnetic field that's relatively weak. The electrons oppose the external magnetic field so much that it weakens it. So when you have a lot of electrons moving around a nucleus, then the nucleus feels a weak magnetic field. Oops. The weaker the magnetic field, the easier it is to flip the nucleus. The only reason the nucleus is in that orientation in the first place is because there's a magnetic field there. If the magnetic field is weak, then it's going to be easy to flip it. If the magnetic field is strong, it's going to be really hard to flip it. The magnetic field is trying to keep it the way it is. And so, if you have a weak magnetic field, let me erase this just to make, for the purpose of clarity. If you have a weak magnetic field, it's easier to flip the nucleus, and so you don't need as much energy to flip the nucleus. If you have a strong magnetic field, you need more energy to flip the nucleus. And so, in sum, the useful thing is that if you don't need as much energy to flip the nucleus, you will absorb lower frequency radio waves. Right? The more often waves hit you, the more energy they carry. If they don't hit you very frequently, they don't carry a lot of energy, and they would flip those. If you need a lot of energy, then you'll absorb higher frequency radio waves. And so now we're able not just to identify whether hydrogens are in a molecule, we can identify every hydrogen that has a different amount of electron density around it. Hydrogens that have a lot of electrons flying, or a lot of electron density flying around them, those will feel a weaker overall magnetic field, and they'll absorb lower frequencies. As you get more and more electron density around a hydrogen, as you get less and less electron density around a hydrogen, as the electrons are stolen away by electronegative things nearby, the hydrogen will feel a stronger magnetic field, and they'll absorb higher radio waves. And so in the spectra that we end up looking at and analyzing, you have an x-axis, and I'll make a separate video for how to analyze these spectra in particular, but conceptually I want you to see how this information is going to be represented on the spectrum. On the x-axis, you end up getting the energy absorbed, where you have the least amount on the right and the most amount on the left. You need less energy absorbed, lower frequencies absorbed, when you have a lot of electrons. Around hydrogen. And you need a lot of energy to flip the nucleus. You need high frequency radio waves if you don't have many electrons, if you have few electrons around a hydrogen. And so what you'll have in these spectra are different peaks. The y-axis is absorbance. Where is light absorbed? Every shadow will be a peak, light's being absorbed, light's being absorbed, light's being absorbed. And each peak will correspond to a certain amount of energy that corresponds to a certain amount of electrons surrounding a hydrogen. So if you had a molecule, for example, like drinking alcohol, you could see that the oxygen is going to steal electrons from this hydrogen here. So it has very few electrons around it, and it will end up showing up further to the left on our spectrum. The hydrogens close by certainly don't feel the effect of that oxygen as much as the one directly bonded to it, but they feel it a little bit. The oxygen funnels electron density towards itself a little bit, even that far away, and so these will have a little bit less electrons around them. And finally, the last hydrogens, the hydrogens over on the far left, they're the furthest from oxygen, so they have all their electrons around them, and so they would be furthest to the right on our graph. And so each of these hydrogens would be in their own electronic environment, so they'd show up as their own peaks here. And the peaks are representing the amount of electrons that are around them, because the amount of electrons determines how much the external field is opposed or not. That determines what the overall magnetic field is, which determines how much energy you need to flip the nuclei. Okay, so that's the general concept behind nuclear magnetic resonance spectroscopy. We're going to see what environments these nuclei are in based on the amount of electrons around them. And so we can use that in order to piece together how hydrogens are arranged in a molecule. So in NMR spectroscopy, we will be shining radio waves on nuclei, see how they flip in a magnetic field depending on their electronic environment, and so we can deduce their electronic environment from that and determine how all of the atoms were put together. So we'll go into more detail on how to do that in future videos.